1904, Chicago Industrial Exposition. The massive single-cylinder engine sat in Hall C like a mechanical pariah. Engineers walked past the exhibit with dismissive glances, shaking their heads at what they considered a fundamental misunderstanding of thermodynamic principles. The Worthington Corliss, Type 14 stationary engine, unveiled by a struggling Pennsylvania foundry, violated nearly every established rule of industrial power generation that had been perfected over 3 decades. Gustav Reinhardt, chief engineer for Pittsburgh Steelworks, stood before the engine with his arms crossed. He'd traveled from Pennsylvania specifically to warn colleagues about this mechanical abomination. "The cooling passages are inaccessible without complete disassembly," he announced to the gathered crowd. "The cylinder head requires removing 14 bolts just to inspect the valves. The crankshaft bearings are buried so deep inside the frame that you'd need to dismantle half the machine to replace them." The engine's specifications seemed designed to frustrate mechanics. A single massive cylinder, 32 inches in diameter, drove a 10-foot flywheel that weighed 4 tons. The cooling system used an unconventional thermosiphon design. No water pump, just natural convection through cast iron passages that wound through the engine block in configurations that defied traditional engineering logic. The valve mechanism sat inside the cylinder head, sealed away from easy maintenance access behind cast iron covers that required special tools even to remove. Traditional stationary engines of the era followed, proven designs developed since the 70s. External valve gear allowed mechanics to adjust timing without engine disassembly. Accessible bearings enabled routine maintenance during brief shutdowns. Simple cooling systems used external pumps that could be serviced independently. These conventions had emerged through hard experience. Factories needed engines they could repair quickly because downtime cost money, production schedules, and customer confidence. The Worthington Corliss design rejected this accumulated wisdom completely. Wilhelm Brenner, the German immigrant engineer who'd conceived the Type 14, believed that preventing failures mattered more than enabling repairs. His integrated cooling passages eliminated external pumps that could fail. His sealed valve mechanisms prevented the contamination that destroyed timing and precision. His buried bearings were oversized by 40%, designed to run a lifetime without replacement rather than enabling easy access for frequent servicing. During the exposition's technical forum, Brenner attempted to explain his philosophy to an audience predisposed toward skepticism. "We don't build engines for mechanics to fix," he stated in his thick Bavarian accent. "We build engines that don't need fixing." The assembled engineers responded with the polite contempt reserved for naive foreigners who hadn't grasped Americans' industrial realities. Richard Morrison from Detroit Machine Works articulated the consensus view in his closing remarks. "Mr. Brenner has created an engine that might run well initially, but when it inevitably fails, and all engines do fail, owners will discover they've purchased an expensive sculpture rather than repairable machinery. The American factory requires practical equipment that mechanics can service in hours, not days. This design represents theoretical engineering disconnected from industrial necessity." The trade journals echoed these criticisms. Industrial Power Monthly devoted 6 pages to explaining why the Worthington Corliss approach was fundamentally flawed. Mechanical Engineering Review published detailed criticisms from established manufacturers who warned that sealed, inaccessible components would strand factory owners with dead equipment when inevitable breakdowns occurred. By the exposition's conclusion, the Type 14 had become the cautionary example of how not to design industrial machinery. The problem that Brenner understood but couldn't articulate effectively centered on a contradiction plaguing American manufacturing. Factory owners complained constantly about engine maintenance costs, yet demanded designs that enabled frequent repairs. This paradox had emerged because existing engines required so much servicing that accessibility had become the primary design criterion, overshadowing reliability improvements that might reduce maintenance needs altogether. Statistics from 1903 industrial surveys revealed the hidden crisis. The average factory stationary engine required major maintenance intervention every 6 weeks. Bearing adjustments, valve timing corrections, cooling system repairs, and governor recalibrations consumed approximately 15% of potential running hours. A typical mid-sized manufacturing facility employing 200 workers lost 3 full days of production monthly simply to service the power plant that kept machinery operating. The economic impact extended beyond direct downtime. Factories maintained dedicated engine mechanics whose entire job involved keeping power plants operational, skilled workers who produced nothing but prevented production stoppages. These positions represented significant fixed costs that factory owners accepted as unavoidable overhead. Parts inventory for common engine repairs consumed warehouse space and tied up capital in components that sat idle until mechanical failures demanded their installation. European manufacturers, particularly British engineering firms, had recognized this efficiency drain but addressed it through incremental improvements to existing designs. Better materials extended bearing life from 6 weeks to 3 months. Improved governors reduced timing adjustments from weekly to monthly schedules. These refinements helped, but accepted the fundamental assumption that engines required regular mechanical intervention to maintain. Performance standards. Brenner's immigrant background provided a different perspective. Growing up in Bavaria's mining regions, he'd observed massive pump engines that ran for months in underground installations where access for repairs was extraordinarily difficult. These machines succeeded not through ease of maintenance, but through rugged construction that prevented failures from occurring initially. When Brenner immigrated to Pennsylvania in 1809 and found work designing stationary engines, he carried these observations into an industry that had evolved along completely different principles. The technical challenge Brenner faced involved balancing competing requirements. Oversized bearings that never needed replacement added weight and cost. Integrated cooling passages that prevented pump failures made the engine more difficult to manufacture. Sealed valve mechanisms that resisted contamination couldn't be adjusted without substantial disassembly. Every design decision that improved reliability made the engine less serviceable, violating the accessibility doctrine that dominated American engineering thought. Financial pressures at the struggling Worthington foundry created unusual freedom for Brenner's unorthodox approach. The company was failing anyway, with revenues declining 40% over 3 years as established manufacturers captured market share. Traditional engine designs weren't saving the business, so management allowed their oddball German engineer to pursue his reliability first philosophy, even though it contradicted conventional wisdom. The first prototype Type 14 engine consumed 18 months of development, emerging in late 1903 as a mechanical statement that reliability could be designed into equipment rather than maintained into it. The massive single-cylinder reduced parts count compared to multi-cylinder designs. The enormous flywheel stored kinetic energy that smoothed power delivery without complex governors. The natural convection cooling eliminated pumps, belts, and external piping that created failure points on conventional engines. But American factory owners weren't asking for reliability. They were asking for serviceability. The consensus held that all engines would break eventually. So smart design meant enabling quick repairs rather than attempting to prevent failures that everyone knew were inevitable. Brenner's Type 14 challenged this assumption in ways the industry wasn't prepared to accept, creating the conditions for spectacular rejection that would almost destroy the Worthington foundry before the engine could prove its unexpected genius. Thomas Cavanaugh had maintained stationary engines for 17 years across 3 continents before arriving at the Milwaukee Grain Exchange in early 1905. Trained at Glasgow's Technical Institute, experienced with British, German, and American designs, Cavanaugh represented the professional mechanic whose opinion shaped purchasing decisions throughout industrial America. When the Exchange's board considered replacing their aging coreless engine with Worthington's new Type 14, they consulted Cavanaugh first. His assessment was devastating. "This engine cannot be maintained by any reasonable definition of that term," Cavanaugh reported after examining Worthington's technical drawings. "The cooling passages exist entirely within the casting, inaccessible for cleaning when mineral deposits accumulate. The crankshaft bearings sit beneath the cylinder, requiring the removal of components weighing several tons before inspection becomes possible. The valve mechanisms are sealed inside the head casting, preventing the timing adjustments that every engine requires after thermal cycling. Kavanaugh created a detailed maintenance analysis that circulated through industrial networks, becoming the definitive criticism of Brenner's design. His report documented that a routine valve inspection on conventional engines required 2 hours and basic hand tools. The same procedure on the Type 14 would demand 14 hours minimum, specialized lifting equipment, and disassembly of structural components that could be damaged during removal. The bearing replacement analysis proved even more damning. Standard engines mounted main bearings in split housings accessible from outside the frame. Mechanics could replace worn bearings during a single shift without disturbing other components. The Type 14's integrated bearing design meant that crankshaft removal required disassembling the entire lower engine structure, a procedure that Kavanaugh estimated would take a full week using factory equipment. Professional mechanics throughout industrial regions began refusing to work on Type 14 installations. The Chicago Mechanical Union issued guidance advising members that Worthington engines represented unacceptable working conditions due to their maintenance-hostile design. The Philadelphia Engineering Society published technical bulletins warning that the Type 14's sealed construction would force factory owners to ship entire engines back to the manufacturer for repairs that mechanics could handle on-site with conventional designs. Samuel Preston, master mechanic at the Camden Textile Mills in New Jersey, became the most vocal critic after his factory reluctantly installed a Type 14 in March 1905. Preston had maintained engines for 23 years, building a reputation for keeping aged equipment running through skilled intervention and regular adjustments. The Worthington engine offended his professional identity. An engine is a living machine that requires continuous attention, Preston explained in technical journal interviews. Bearings need adjustment as wear occurs. Valves need timing corrections as seats wear. Cooling systems need cleaning as deposits accumulate. Mr. Brenner has built an engine that assumes none of these realities matter, that somehow his design transcends the mechanical facts that govern all. Machinery. This is engineering arrogance that will cost factory owners dearly when inevitable failures occur. The technical arguments gained support from established manufacturers who saw Worthington's unconventional approach threatening their market position. Corliss Engine Company circulated comparison studies showing their designs required 1/3 the disassembly effort for routine maintenance. Westinghouse published engineering analyses demonstrating that accessible components reduced total ownership costs despite requiring more frequent service interventions. By mid-1905, the Worthington Type 14 had become industrial persona non grata. Factory purchasing agents received explicit warnings from their maintenance departments. The engine's design guaranteed expensive problems that would multiply as the equipment aged. Insurance underwriters questioned whether to cover installations of equipment that couldn't be properly serviced. Mechanical engineering schools used the Type 14 as a teaching example of how theoretical design divorced from maintenance realities created impractical equipment. Wilhelm Brenner watched his creation being professionally destroyed by the very experts whose approval determined commercial success. He understood their concerns but believed they reflected assumptions based on inferior designs rather than immutable mechanical laws. The challenge was that Brenner couldn't prove his engine wouldn't need the maintenance that mechanics insisted all engines required. Not until years of operation provided evidence that his radical approach had been correct all along. The first catastrophic failure occurred at the Hammond Lumber Mill in Oregon during July 1905, just 4 months after installation. The Type 14 engine seized completely during peak production, the massive flywheel grinding to a halt as internal components fused together under conditions that terrified everyone who witnessed it. Black smoke poured from the cylinder head as superheated oil ignited inside the crankcase. The mill's superintendent ordered immediate shutdown of all operations while mechanics attempted to diagnose the failure. Investigation revealed a problem that validated every criticism mechanics had raised. The cooling system had developed an airlock in the thermosiphon passages, preventing water circulation and causing catastrophic overheating. With conventional engines, mechanics would have detected this problem through accessible temperature gauges and external cooling pipes. The Type 14's integrated design hid the developing crisis until sudden, complete failure occurred. The repair consumed 3 weeks. Worthington Foundry sent their senior engineer to supervise the disassembly, which required building temporary scaffolding to support the cylinder head during removal. The internal cooling passages showed scale deposits from poor water quality, contamination that would have been visible and cleanable in external cooling systems, the crankshaft. Bearings had melted from extreme temperatures, requiring complete replacement of components that mechanics insisted should have been inspectable before catastrophic damage occurred. Hammond Lumber's experience became a warning distributed throughout the Pacific Northwest timber industry. Letters between mill superintendents described the nightmare of having their primary power source completely disabled with no reasonable way to diagnose or repair problems before total failure. The consensus, Brenner's sealed design, was exactly the disaster that professionals had predicted. The second major failure struck the Cincinnati Machine Works in September 1905. Their Type 14 developed a mysterious vibration that grew progressively worse over 2 weeks until the engine automatically shut down through its overspeed governor. The mechanical team spent 6 days disassembling the engine to discover that a single valve spring had fractured, a component that would take 15 minutes to replace on conventional designs with external valve gear. The Cincinnati incident emphasized another criticism. The engine's sealed construction meant that minor failures became major disasters. The broken valve spring had allowed the valve to contact the piston, damaging both components and requiring extensive machining to repair. With external valve mechanisms, mechanics would have noticed the spring failure immediately and replaced it before collateral damage occurred. By early 1906, Worthington Foundry was receiving cancellation demands from customers who'd ordered Type 14 engines before the failures became widely known. Factory owners who'd already installed the equipment were demanding refunds or replacement with conventional designs. The company's financial position deteriorated rapidly as legal disputes over warranty obligations consumed resources that had been earmarked for production. The trade press documented Worthington's collapse with analytical pieces explaining how engineering hubris had destroyed a once respectable foundry. Mechanical World published a comprehensive post-mortem titled "The Cost of Ignoring Maintenance Reality," which became required reading in engineering schools. The article concluded that Brenner's attempt to eliminate maintenance needs had instead created equipment that couldn't be maintained at all, the worst possible outcome. Insurance companies began refusing coverage for Type 14 installations, classifying the engine as inherently high risk due to its maintenance-resistant design. This decision effectively ended new sales, as factory owners couldn't operate uninsured equipment. Mechanical supply houses stopped stocking Worthington parts, forcing the handful of existing installations to order directly from the foundry with extended lead times. Wilhelm Brenner faced professional destruction. His radical design had failed exactly as critics predicted, vindicated the conventional wisdom, and potentially bankrupted the company that had trusted his vision. Standing in the Worthington factory amid the wreckage of his reputation, Brenner couldn't understand why real-world results contradicted his engineering calculations. The sealed design should have prevented contamination. The oversized bearings should have eliminated wear problems. The integrated cooling should have been more reliable than external pumps. Something fundamental wasn't matching between his design intentions and actual operating conditions. Robert McAllister didn't contact Worthington Foundry about his experience because, frankly, his Type 14 engine had nothing wrong with it. The owner of a small textile operation in rural Vermont, McAllister had purchased one of the first production units in early 1905, installing it in a mill building that powered 30 looms through an overhead line shaft system. His mechanic had warned against buying Worthington equipment, but budget constraints left few options. 2 years passed. Then 5. The Hammond Lumber disaster and Cincinnati failures circulated through trade networks, but McAllister's engine ran continuously through every production shift without incident. The massive flywheel maintained steady power delivery. The thermosyphon cooling cycled water silently through the integrated passages. The sealed valve mechanism operated with metronomic precision. McAllister performed the basic maintenance Brenner had specified: weekly oil level checks, monthly grease fittings, annual cooling water replacement. Nothing more was needed. By 1910, McAllister's Type 14 had operated for 5 years without a single maintenance shutdown. This contradicted everything the mechanical establishment had predicted, yet nobody was tracking it because the engine simply worked without demanding attention. In an era when engines routinely required intervention every 6 weeks, the Worthington design's most remarkable feature was how completely it disappeared from operational consciousness. Similar stories were emerging in scattered installations across North America. A grain elevator in Manitoba reported 7 years of continuous operation with minimal service. A small steel fabrication shop in Pennsylvania discovered their Type 14 outlasting 2 conventional engines that had been installed simultaneously in adjacent buildings. A Midwest creamery found that their Worthington engine consumed half the maintenance budget of comparable equipment at competing facilities. The pattern became clear to careful observers. Installations with clean water sources, competent initial setup, and basic routine maintenance were experiencing essentially trouble-free operation. The early catastrophic failures had resulted from poor water quality causing cooling system scale buildup, improper installation creating mechanical stresses, or complete neglect of basic service procedures. When operated according to Brenner's specifications, the Type 14 performed exactly as designed. It simply didn't break, James. Whitmore, a mechanical engineer consulting for insurance underwriters, began investigating this contradiction in 1911. His survey of 47 Type 14 installations revealed a stark division. 9 engines had experienced serious failures within the first 2 years. These were the disasters that had shaped the engine's reputation. 38 engines were running continuously with remarkably low maintenance requirements. The failed installations shared common factors: untrained operators, poor water quality, inadequate initial commissioning. Whitmore's report challenged the prevailing wisdom directly. The Worthington Type 14 does not fail frequently, he concluded. It fails spectacularly when improperly installed or operated, creating memorable disasters that overshadow dozens of successful installations running quietly in obscurity. The engine's sealed design prevents minor problems from being corrected before they become catastrophic, but it also prevents most problems from developing in the first place. The foundry had collapsed by the time this evidence emerged. Worthington closed in 1908, unable to survive the commercial damage from early failures. Wilhelm Brenner had returned to Germany in disgrace, never learning that his radical design was slowly vindicating itself through unglamorous success in installations that nobody was documenting because successful equipment doesn't generate reports. The irony deepened as years accumulated. The supposedly unfixable engines continued running, while conventional designs that had replaced them required the constant maintenance that mechanics had insisted was normal. Factory owners who'd kept their Type 14 installations discovered they'd accidentally purchased the most reliable industrial engines of their generation, not through any quality that mechanics valued, but precisely because the sealed design prevented the wear patterns that conventional engines experienced. By 1920, the oldest surviving Type 14 installations had operated 15 years without major failures. The massive single cylinders showed almost no wear. The oversized bearings maintained their original clearances. The thermosiphon cooling systems continued circulating water without pumps that could fail. These engines had become mechanical anachronisms, outdated by newer technologies, yet consistently outlasting equipment that had superseded them commercially. The Great Depression forced factories to extract maximum value from existing equipment. Maintenance budgets collapsed. Replacement purchases became impossible. Across industrial America, aging machinery was pushed beyond normal service life as companies struggled to survive economic catastrophe. This crucible would ultimately reveal the Type 14's most remarkable characteristic: its ability to continue operating under conditions that destroyed conventional engines. The McAllister textile mill in Vermont exemplified this unexpected endurance. By 1935, Robert's son Thomas was operating the business under Depression conditions that had eliminated discretionary spending entirely. The Type 14 engine, now 30 years old, continued powering production without the bearing replacements, valve overhauls, or cooling system refurbishments that conventional designs would have demanded. Thomas kept detailed records showing the engine had consumed exactly $127 in maintenance costs over 3 decades, mostly for basic consumables like oil and grease. Comparable conventional engines installed in neighboring facilities had been replaced multiple times. The pattern was consistent. External valve gear wore out and required rebuilding every 8 to 10 years. Main bearings needed replacement every 5 years. Cooling system pumps failed every 3 years. Each intervention generated cascading additional maintenance as mechanics discovered related problems during disassembly. The total ownership cost for conventional designs exceeded the Type 14s by factors that nobody had anticipated when criticizing Brenner's approach. Industrial surveys during the mid-1930s began documenting these long-term performance patterns. Engineering consultants found that surviving Type 14 installations were providing extraordinarily low-cost power generation precisely because they didn't require the maintenance that had been considered inevitable. The sealed designs prevented the gradual deterioration that plagued accessible components. The massive, slow-turning construction minimized wear rates. The integrated cooling eliminated the external systems that failed regularly on conventional equipment. The Manitoba grain elevator's experience became legendary in regional industrial circles. Their Type 14 had operated continuously from 1906 through 1938 without a single internal inspection. 32 years of grain processing without opening the engine's crankcase. The only maintenance performed involved oil changes, grease fittings, and replacing external gaskets as they aged. When the elevator finally shut down due to railroad route changes, the engine's new owner disassembled it out of curiosity, discovering internal components still within original manufacturing tolerances. Academic interest in the Type 14 phenomenon emerged from MIT's Mechanical Engineering Department in 1936. Professor Harrison Mitchell conducted metallurgical analysis of components from engines with 2 and 3 decades of operation. His findings challenged fundamental assumptions about engine wear patterns. The Type 14's slow rotational speed, just 120 RPM compared to 300 to 400 RPM for conventional designs, created boundary lubrication conditions where oil films protected metal surfaces more effectively. The oversized bearings Brenner had specified distributed loads across larger areas, reducing pressure and wear rates proportionally. Mitchell's most significant discovery involved the thermosiphon cooling system that mechanics had criticized as unmaintainable. The sealed passages actually prevented the mineral accumulation that plagued external cooling systems. Because water circulated continuously through closed loops rather than open reservoirs that concentrated minerals, scale formation occurred at rates 10 times slower than conventional designs. The inaccessibility that mechanics feared actually contributed to longevity by preventing contamination that external systems couldn't avoid. By 1940, the oldest Type 14 installations had operated 35 years, longer than most factory buildings constructed when the engines were installed. Stories circulated about engines outlasting their original purposes. A Pennsylvania steel fabrication shop had converted to automotive parts manufacturing in the 1920s, completely changing their production processes while the Worthington engine continued providing reliable power. A Wisconsin creamery had transitioned through 3 different owners and multiple process updates without ever needing to replace or significantly service their Type 14. The wartime production surge of the early 1940s created final validation. Factories that had kept Type 14 installations found themselves with competitive advantages as maintenance resources became scarce. Engines that required minimal intervention continued operating while conventional designs struggled with delayed repairs and parts shortages. The supposedly unfixable equipment proved easiest to maintain under crisis conditions because it simply needed less maintenance overall. Wilhelm Brenner had died in Bavaria in 1923, never knowing his rejected design had quietly revolutionized industrial reliability through principles the mechanical establishment had condemned as impractical. The engines he'd built to run without maintenance were proving they could do exactly that, not because they were easy to fix, but because they rarely needed fixing in the first place.